This video will address section 4.9, which is all about the antiderivative. So we're going to learn how to perform the inverse operation of derivatives. So that's what an antiderivative is the inverse operation of a derivative. So just like addition and subtraction are inverse operations, so are taking the derivative of a function and then taking its antiderivative. So let's say we have a function f of x equals 3x squared plus 7. And if we take its derivative, we would get the function 6x. So if we wanted to reverse that process, and we wanted to take 6x, the function, and determine what initial function we had that we took the derivative of that got us an answer of 6x, we have to do some backwards thinking. So if you think about the power rule and how it works with derivatives, we're taking the 2 and we're multiplying it by 3, and then we're subtracting 1. So when we do an inverse of that, we need to first of all reverse the process and then reverse each operation. So what I'm going to do first is I'm going to take the exponent of 1 and I'm going to add 1 to it, and then I'm going to divide by that. So what that will give me is x squared times the 6 divided by that exponent of 2, which simplifies to be 3x squared. So I undid my process of the power rule, and again that is taking an antiderivative of 6x so that we get back to this original function. But you can see here that we only ended up with a 3x squared, and we are basically off by a constant. So what we'll do with the antiderivative is we'll add c being a constant, to our answer. And so the reason that we're not actually addressing the 7 and instead just using a c is that if I changed this original function around just a bit and I made it 3x squared minus 4 and took its derivative, it turns out I'd get the exact same function, 6x. So performing the antiderivative operation, I would once again get 3x squared plus some constant c. So essentially, there are an infinite number of original functions f, depending on whatever constant I have added to the end, whose derivative will all be the exact same function, 6x. Which means that when I take the antiderivative of 6x, there will be an infinite number of functions that exist to represent that original function, and therefore the constant c is used to represent any value that can be added to the end to create that antiderivative. All right, so in terms of notation, we know that if we use d over dx, the derivative with respect to x of a function f of x, that we get f prime of x. So this is our derivative notation. And the antiderivative notation is this symbol right here. So if we took the antiderivative of f of x, of f prime of x, with respect to x, then we'd get back to our original function, f. So this is our notation here for antiderivative. And the symbol is called an integral. And we'll actually relate the antiderivative to the integral in the upcoming sections this week. But you'll notice that you have to show which variable you are taking the antiderivative with respect to. so that dx does that for us. All right, so a little bit more notation here. The function that we are taking the antiderivative of is going to be called the integrand. And the dx is going to give us information about the variable of integration. So we've got the integrand, which is the actual function that we're taking the antiderivative of, and then we have the notation that tells us with respect to which variable we're doing that. All right, one other thing to note is that here, when we talk about integral, we are talking about the process of integration. And it's important to note that here we're talking about the indefinite integral. And the only reason I mention that is because in the future we'll reference the definite integral and we'll compare the two. So I just wanted to bring up the notation right now. But indefinite integral means that you're not going to see any start and end values over the integral. So it's not going to be over a specific interval for the function, but an open-ended interval. So that's called indefinite integral. All right, let me define the power rule. So I used it up above, and again it's just the inverse operation of the power rule for derivatives, but let me define it in explicit terms. So let's say that I'm taking the antiderivative of some exponential function x to the p. Power function, I mean, not exponential function. This is a power function. And I'm doing it with respect to the variable x. In order to undo the derivative, or take the antiderivative, what I need to do is I need to raise the power by an increment of 1, and then I need to divide by that power, not forgetting to add some constant c to represent the infinite number of original functions that we could get when we take the antiderivative. There are a couple of other rules as well. We have the constant multiple rule. And again, this is the constant multiple rule for integrals. But basically, if you are taking the antiderivative of some function, and that function is being multiplied by a constant a, then you are allowed to take that constant a and write it as a multiplier of that integral. So just like with derivatives where you can factor out the constant and work with the rest of the function finding its derivative, you can do the same thing with antiderivatives. One more rule. We have the sum rule for integrals. So the sum rule addresses the scenario of taking the antiderivative of two functions being added or subtracted, and it turns out that you are allowed to separate those into two different integrals or two different antiderivatives. So I can integrate the function f with respect to x, and then I can also integrate the function g with respect to x, and then I can add those two results together. And again, the same thing applies if it were subtraction. All right, so we've got all of our rules set. Let's take a look at some examples. And most of this is really just about using some backwards thinking. If you know how to take the derivative of every type of function, then you should know how to take the antiderivative as well. So So here's my first example. We are taking the antiderivative of this function that has 3 terms, and we're doing it with respect to x. Remember, it's important that you know which variable you're integrating with respect to, and I'll show you why in just a second. Now, I'm also going to utilize the sum rule as well as the constant multiple rule in order to rewrite this integral. So I can separate this into 3 separate terms, or 3 separate integrals or antiderivatives. And so the first one, I'm going to also factor out that constant multiple. And I'm going to integrate x squared with respect to x and multiply my result by 3. And I'm going to add that to the antiderivative of 2 with respect to x. And I'm going to subtract 5 times the antiderivative of the square root of x with respect to x. Now this is something that I would typically do in my head and not actually write out every step. But as you're practicing these, you really have to earn the right to be able to do this in your head. You've got to kind of write all the steps down until you're really comfortable and feel like you can shortcut a little bit. So if I integrate or take the antiderivative of this particular piece, I can use the power rule. I can add 1 to the exponent and then divide by that exponent, not forgetting that I also have a constant multiple of 3 here. And to that I need to add some constant c. So if I simplify that, the 3's cancel and I get x cubed plus c for my first term. Let's move on to the second piece. Now, something you might consider here is that taking that 2 and writing it as a constant multiple can be done as well, except that all you're left to integrate is just 1. So you might want to think about that in terms of x to the 0 power. If we don't have an x in all, then we have an x to the 0 power. And so you can still use that same idea of adding 1, that power rule, adding 1 and dividing by 1. And so you get x. Now don't forget to take that and multiply it by 2, and then of course add c. So my second term, I'll add 2x plus c. And it's always a good idea to just double check these. They're so quick to take the derivative of each one, and that would be a check to make sure that your antiderivative is correct. So take the derivative of x cubed and you get 3x squared, which is good because that's what we started with. Take the derivative of 2x and we get 2, and again that's what we started with. When you take the derivative of constants, remember those are just 0, which works out perfectly. Let's go on to that last term, and here you might want to take that square root and write it as a fractional exponent so that you can once again use that power rule. So I'm going to add 1 to 1/2. You've got to do some quick fraction work here. 1/2 plus 1 is going to be 3/2. I'm going to divide by 3/2, and then I'm of course going to multiply by that 5 and add a constant. So there's some cleanup to do here. First of all, I've got 5 divided by 3/2. And remember that's equivalent to 5 times 2/3, which is 10/3. So I've got minus 10/3 x to the 3/2 power. And then I've got a constant added to the end. Now, you could write that as the square root of x cubed. You could put it back into the radical form. Either way, it doesn't matter. So we have our answer here. Essentially, we've got the antiderivative of the first term added to the antiderivative of the second term, and then we have a subtraction here because of the original sign in the problem, and the antiderivative of that third term. Now, the only thing to note here is that if you have 3 constants, let's say this is 2, 5, and -7. Whatever they are, it doesn't matter. Anytime you add 3 constants together, let's call them C1, C2, and C3, the sum of any 3 constants is still just a constant. So I can write the final answer with that constant added to the end of the entire piece. So I can just add one constant to the end of it all without writing 3 individual constants. So there's a good idea of how to use the product rule, the power rule, the constant rule, and the sum rule for integrals.